What that means is that if something is polar, a polar solvent, so it has a dipole moment associated with it, or even hydrogen bonding, it's going to better dissolve or mix with another solvent that is also polar, so has a dipole in it, or is ionic. So like an ionic compound is going to dissolve better in a polar solvent. Okay, so like dissolves like. Polar is going to like other polar things. Anything where there's a difference of charge. And then non-polar is going to like other non-polar. So think of your typical like hydrocarbons. Remember, carbon-hydrogen bonds are completely non-polar. So if I look at my particular solute for this first one I'm trying to dissolve, it's a iodine molecule, which is iodine bonded with iodine. There is completely non-polar. The only kinds of intermolecular forces are going to be dispersion forces. So iodine is going to dissolve better in a solvent that only has dispersion forces rather than something that has dipole-dipole intermolecular forces. So out of the options here, I'm going to go for this guy. It's all just carbons and hydrogen. It doesn't even matter if I don't know what it's called or what it looks like. Okay, the point is I know that water is a polar molecule, right? I know that we've got hydrogen, oxygen, hydrogen. Hang on. I'm going to draw it this way just for fun. I was going to draw it the other way up, but you know what? I'm going to do it this way. So we know that the OH bond is polar. We know that oxygen has two lone pairs on it. Therefore, we know that this molecule, I just totally draw an oxygen instead of a hydrogen. What is wrong with me today? More coffee required. Let's see if I can just erase you and only you. No, they're all going to go, oh, whatever. More coffee required. There is never enough coffee in the whole world for my needs. Right. So then we'd have two lone pairs on the oxygen as well. Is there an easy way to do lone pairs? No, there is not. So 1, 2, 3, 4. That looks terrible. So we know there's a delta minus delta plus, and this is a very polar molecule. So that's going to dissolve ions better or other polar solvents. Okay, so what about this guy right here? The second option, I am going to zoom in on you right here. Look at that. Oxygen with lone pairs of electrons bonded to a hydrogen. That is going to be polar, right? In fact, that is going to be so polar it can have hydrogen bonding interactions. So then if I look at my two options, my CH3OH, well, that has a OH group on the end as well, okay? So that, again, like dissolves like. This is the more polar option, right? So this whatever this is, this solute is going to dissolve better in methanol than in the diethyl ether because this is non-polar, okay? So again, we're looking at something that is polar versus non-polar. So that is the key to these kind of questions. I should just copy and paste. I've now realized that would have been far more efficient. Okay, so the last one, sodium chloride, that is an ionic compound. It's going to break up into the sodium ion and the chloride ion when dissolved in a polar solvent like water. So water would be the option here. That is polar. Oh, whoops. Yes, check, check, check. The water would be polar, would dissolve the ionic compound much better than something that is non-polar. All right, so hopefully that is helpful for you guys to try and work out what is like dissolve like. When we say like dissolve like, it means polar likes polar things. So charge differentiation, bond dipoles like ionic compounds. Non-polar likes non-polar, so you can't dissolve like sodium chloride in something like benzene or toluene or some massive hydrocarbon. Okay,